two thickness. Okay, you have thickness on the left hand side, thickness of the right hand side. You have twice of 0.02. What will happen is now your shear xy will be equal to Vy over Izz, right? 80 times 10 to the power minus 6 divided by twice 0.02. So this will be equal to Vy over Izz, okay? So 80 power minus 6 divided by 2 divided by 0.02, and this will be equal to 2 times 10 to the power minus 3, okay? So the correct value to use is this value. Why? Because it has a higher what? Stress value. And it has a higher stress value because it has a what? It has a smaller thickness, right? Because if you look at point A, right? If you look at point A, it's at the intersection between 160 and twice of what? Twice of the 20 millimeters thickness. So you calculate for the thickness, or you calculate based on the smaller thickness, which you get higher value. Okay. Now point A is the easy part. Now point B. Point B is where things get tricky, but not impossible. Okay. So let's look at point B. So if we now turn our attention to point B, okay. Now point B, there are a few options that you can take. Okay. I'm going to sketch our datum first. So over here, this is our datum. Okay, over here, that's our datum. And then I'm going to, okay, that's our datum. I'm going to use our pointer. Okay. Okay. To calculate point B, what area do we take? Okay, what area do we take? Okay, so we want to determine at point B. Okay, okay, so what area do we take? So all of us know Vy is coming from the top. Okay, Vy is coming from the top. Okay, so one possibility, so we all know Vy is coming up from the top. One possibility to calculate point B, we take this whole thing. Or I'm going to shade that. So we consider this whole area. Okay. Or we consider just this area. Or we consider just this area. Okay. So there are three possibilities. Okay. And I'm going to write the rules. Okay. So the rules is the what? The rules is the datum is at the centroid. Right? Analysis starts from the distance furthest away from the centroid. And third, the first moment of area cannot cross the centroid. Okay. Right. By looking at all these rules, right, we know that, so I'm going to label this option 1. Okay, so I'm going to call this optional. So option 1 is not correct, it's wrong, right? Option 1 is okay, it's not right. Any idea why? Which rule has it broken? Anyone, you can write down. Okay, write down in the chat or you can say something. Why option 1 is not right? Anyone? Yeah, you're absolutely right. It crossed the what? It crossed the centroid. So cross centroid. Or Q cross centroid. Okay. Option number 2. This is also not right. Why? Option 2 is also wrong. Any idea why? Did it? The datum, right? Sorry, the centroid. Okay, the first moment of area did not cross the centroid. That's for sure, right? So it's okay. But what rule did it break? So remember what I told you? The analysis has to start from where? Start from Y max. So now the Y max is at the bottom now, right? So analysis starts from the Y max. Okay, so analysis did not start from Y max. So that's why it failed. And the third one, option number 3, is correct because the analysis starts from where? Y max. Okay. This is a typical example that you can see, right? That you cannot break any of the what? Any of the rules at all. You break the rule, we are done. Okay, we are so-called game over. Okay, we are done. Okay. Now, okay, so this is a very critical example that you have to know. Okay, because if you don't apply all these rules, you get confused very easily. Okay, and when I've been teaching this course a lot of times, okay, and I see students get confused very quickly. Okay, if you don't have these rules set right. Now, then the next thing I want to highlight is we are going to look at the formula that we have derived, and we are going to come back to this cross-sectional view again. Okay, that we've just done. So remember, we derived that shear xy is equal to 3/2 vy over a, and then we have 1 minus by y squared over c squared, right? Right, we derive this, and what we realize is based on this configuration, right? Right, based on this configuration over here. So based on that formula, I'm now going to sketch the shear stress distribution. Okay. So if we were to sketch our shear stress distribution now, so I'm going to sketch some lines over here. Right. So this is our shear xy, and this is our y direction. Okay. And by looking at that formula, the parent function, this is basically a second order polynomial equation. Okay. And it will look like this. So if I'm going to sketch this out, it will look like this. And what you realize is this position is at the tau max. And at this position, at 0, this is the position of our centroid. Right? So it's different from bending moment, right? Bending moment, the normal stress, right? At the centroid, the for centric bending, right? The shear stress, the normal stress is equal to 0. So if we look at bending moment function, we have stress X is equal to mz, for example, over izz multiplied by y. So if we have our normal stress, and then we have our y function, right? So this is our normal stress X, and then this is our y. We're going to assume the direction is this way. Okay, so if I'm going to sketch this out, okay. So due to normal stress at bending, and we know that at this position again is at the what? Centroid. At the centroid, stress X is equal to what? 0 due to bending moment. In shear, the maximum is at the what? The maximum is at the centroid. Okay, the maximum at the centroid. So I want you to know this. If you were to look at the function over here, right? If the thickness is constant, right? When only when the thickness is constant, when thickness is constant. Either you do the analysis from the top or the analysis from the bottom, right? The tau max will always be the same. Okay. So let's look into perspective. Let's look at how to determine, with the example that we are doing now, how to determine the first moment of area. Okay. So let's put in some numbers now. Let's put in some numbers. So I'm going to, okay. So we are coming back to this example again, right? So we want to determine, now we want to determine the, okay, we want to determine, the shear stress at the centroid. Okay. So we are aware that the centroid is 35 millimeters from the top. Right. So we are going to use two methods. Okay. We're going to find the shear stress at the centroid. Okay. By using the top section. Okay. By focusing on the what? On the top section. So this is the top section. And then this is the bottom section.